What's up, guys? Welcome back to Angel's Trivias. So, before I go to school, I just want to quickly share with you a knowledge about light as a wave and as a particle. If you want to know what's on that video, just keep on watching.
We the best music! Another one.
Is light a wave or a stream of particles? Very noteworthy and distinguished physicists have taken up each side of the argument, providing a wealth of evidence for each side. The fact is that light exhibits behaviors that are characteristic of both waves and particles. The first part of the clip will be on the wave-like nature of light. Light exhibits certain behaviors that are characteristic of any wave and would be difficult to explain with a purely particle view. Here are some characteristics of wave that goes the same with light. First, light reflects in the same manner that any wave would reflect. Second, light refracts in the same manner that any wave would refract. Third, light refracts in the same manner that any wave would refract. Fourth, light undergoes interference in the same manner that any wave would interfere. And fifth, light exhibits the Doppler effect just as any wave would exhibit the Doppler effect. Light behaves in a way that is consistent with their conceptual and mathematical understanding of waves. Since light behaves like a wave, one would have good reason to believe that it might be a wave. Light as a particle. Light behaves mainly like a wave, but it can also be considered to consist of tiny packages of energy called photons. Photons carry a fixed amount of energy but have no mass. The energy of a photon depends on its wavelength. Longer wavelength photons have less energy, and shorter wavelength photons have more. Red photons, for example, have less energy than blue ones. Until about 1900s, scientists only understood electromagnetic radiation to be made up of waves. Then Max Planck and others were studying the photoelectric effect, and they found that certain types of metal and other materials will eject electrons when light shines on them. They expected that the number of electrons ejected from the metal would increase with the intensity of brightness of the light directed towards the metal. What they found instead was that the wavelength of the light was what affected the number of electrons ejected. More energetic wavelengths such as blue and ultraviolet caused more electrons to be ejected than red or infrared wavelengths. They also found that increasing the intensity of light increased the number of electrons ejected, but not their speed. Planck realized that the energy of the electromagnetic radiation was proportional to its frequency, but admitted that he didn't understand why this was the case and said it was lucky guesswork. Einstein was the first to explain what was happening. He theorized that electromagnetic energy comes in packets, or quanta, which we now call photons. So light behaves as a wave and as a particle, depending on the circumstances and the effect being observed. This concept is now known as wave-particle duality. For some time, we have known that light is both a particle and a wave. At least, it behaves like a particle and a wave. However, seeing both at the same time is no easy feat. For decades, scientists have been trying to directly observe both of these features. Now, they have finally done it. For the first time ever, scientists have captured a snapshot of this duality. That's it, guys. Subscribe to my YouTube channel for more trivias from me. Thank you for watching.